Now, what was I saying before I got so rudely cut off by me not turning my phone so it wouldn't shut off? My phone shut off. Let's continue. Back to where we were. Talking about stars. What is a star? Are there shooting stars? How is this like a star? Look at all the colors. Notice these details. We were talking about stars being kind of like male height, right? Short, tall, good for gymnastics. Probably difficult actually to play basketball. It's difficult if you're that tall. Hard for the heart and so on. So most stars being in here, fewer and even fewer. The difference being how much gas there is, and so how much mass there is. So what do you think? If you have more mass, more gravity, stronger squeeze, things start snapping together faster, shorter lives versus less mass, less gravity, slower fusion, a little gentler, much longer lives, much longer, much shorter, big range. You can look that up. Which ones are going to be hotter? Which ones are going to be the raging fire? Not burning really, it's fusing. Which ones will be hotter? Which ones will be cooler? Will it be a range? We're going to plot this on the HR diagram, but we started talking about this. Remember that temperature is related to the color. The color we see is a combination of frequencies, right? A combination of frequencies that give it the overall appearance of being red or red-orange, right? And the combination of frequencies, like all the frequencies of visible light, we would see as white. Lower frequencies, higher frequencies. Higher frequencies, hotter. Hotter. Fusing faster. Fusing slower. Hotter. All frequencies with a lot of high frequency blues. White with blue, blue-white. All frequencies. Hot. Make something white hot, that's hot. Blue, white, hot. Really hot. Glowing yellow, that's hot too. You see a stove top, electric range top, be red, orange. It'll actually glow in the green too. Hot, hotter, 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 really hot. Why? It's connected. These are the connections. If you understand this, you understand quite a lot, right? Low mass, high mass, very high mass. And so in around 1900, a couple of famous women stood out in the Harvard calculators, or the Pickering women. They worked for this guy named Pickering, and I won't go into that. That's an interesting story, and that was before the women's rights movements, but they were big in what they did and what they continued to do. So these women in this group, like, oh, you go work on this. Well, they did, and they made some tremendous discoveries and blew open our world, as I've mentioned before. And also, hopefully, and did blow open some minds, at least, to the fact that women are every bit as capable as men in doing this stuff. You just have to want to do it. Not all men want to do it, not all women want to do it, whatever, but they're very capable. And what people were doing was taking the light that's given off by stars and breaking it down, as we've discussed. Wiens Law, right? I'm talking about Wiens Law here too, breaking down the light and finding out the brightest frequency that's given off, and that'll tell us the temperature when you put it into the Wiens equation, Wiens Law, it'll tell us the temperature. But early on, you know, the telescopes weren't great, and the imaging wasn't great on sort of glass plates, and they had to look at this stuff, and those women were analyzing these plates, and one of them, Annie Cannon, her mother's maiden name was Jump, Annie Jump Cannon, like jumping over kids. It's a cool name. But she looked at these plates, and these plates were kind of organized, and they were looking at the light, and they were looking at the images, and they were organized according to, you know, some similarities, and they were alphabetized, right? A, B, C, D. And she really was thinking, and this takes a lot of subtle awareness and insight to figure out what's going on. And so she was thinking about these groups and what's similar about these plates and these plates. So kind of rearranged the alphabet, you know, worked on the groups. She realized that if you put them in a different order, it might tell you something. Temperature has a lot to do with it. Turns out when the gas is hotter, it tends to rip off electrons, and that changes the light that comes off the spectrum. Anyway, there's a connection between the temperature and the color. We said that. But there's other things, right? And so she rearranged the piles. And so you see the alphabet here has got mixed up. There's no particular meaning to O or A or F or G, except there were piles rearranged. You could make up other letters, but I think that's an interesting story. And when she did this, she made up a memory aid, because memory aids are useful. And our memory aid was O, B, A, fine, girl, kiss, me. You could use guy, whatever, O, B, A, fine, girl, kiss, me. And that's the memory aid, girl or guy. O, B. Now, how do you remember that these are the blue-white ones, O and B? The blue-white ones from very high mass, blue, short lives. How do you remember? Well, I add to this and I say, ouch, burn. Ouch, burn. O, B, A, fine, girl, kiss me. Or whatever you want to do with that. Where's my, there it is. And I say, how do you know the KM? Well, that's going to be cool, man. We're going to revisit this, so that's my little added, cool man, outsburn, cool man, that's how it goes. All right, so we're going to connect those on the HR diagram, which is going to tell us a lot about stars. Brilliant, Hertzsprung, and Russell. All right, let's go on over here. So there's connections. Those connections go a long way. You know a lot if you're doing that. Zoom it in. Let's talk about, we've talked about the range of stars. We've talked about the range. Now, there's something interesting, though. When we think about how wide a range those stars are, right? Stars all start the same way. So it's a big gas cloud, right? And out of this enormous, giant molecular cloud, inside of a galaxy, somewhere in a galaxy, right? This is a just crazy cloud becoming a galaxy. And then within there are these giant clouds. And within those giant clouds, many stars form. And as a star is forming, The gas is pulling together slowly, but it's got time. Pulling together. Before the fusion starts, it's not really a star, is it? It's not a star until it starts fusing. It's not a star unless fusion's going on. So before that, it's called a protostar, becoming a star. And what else might be coming as this spinning gas cloud starts coming together? Oh yeah, most of the gas is going to go to the center, and around it, planets and moons and leftovers, right? And motorcycles. So, protostar. But then, all stars, no matter how big, right? 5 foot to 8 foot. No matter how big, all stars, no matter how much gas they start with, 200 times the sun or 1/10 as much as the sun. Right? 75 Jupiter's worth, that's enough, something like that. All stars, no matter how much mass, start life. We call it life. It's not a living organism as we think of it, but we start life or existence as a star. They start fusion the exact same way. And they start doing the same thing. And there's a reason, and I've got an analogy for you. And they spend most of their lives, almost all of their lives, in this first stage of life, or this first fusion stage, first fusion cycle. Okay, so why? Why is that true? Why do stars start the same way? So I was thinking about this in writing the book, and just popped into my head this old Saturday Night Live skit. This is the idea. Gravity pulls in, right? Not fusing yet. And I thought of this skit, Dan Aykroyd, if you know Ghostbusters, or if you know Blues Brothers, old movies that are both fun. Dan Aykroyd was in the early Saturday Night Live. And there's a skit where he's being interviewed, and he's a toy maker. So it's like a news interview, and she's interviewing him, and she's saying, not all toys are safe for children, and there's a movement to make toys safe for children, but a lot of your toys are not very safe. I mean, what do you have to say about that? And he says, well, what do you mean? What do you mean? My toys are perfectly safe. I mean, look at this. Look at this. Look at this bag of glass. It's like a plastic bag filled with broken glass. What is this bag of broken glass? That's perfectly safe. Kids love it. They roll it around. They make all these different noises. Kids love this. I thought about that broken glass. Imagine taking a bag of glass, all kinds of glass, broken glass, and squeezing it. Hopefully it's a canvas bag, right? And you squeeze. What's going to break first? The ones that are more easily broken. The cheap glass, the easy to break glass. Whatever's easiest to break when you squeeze will always break first, won't it? Whatever's easiest to fuse will always fuse first. No matter how much gas you start with, when that comes in as a protostar, the first thing to snap together are individual protons, single. That's the first stage of life. It's called the main sequence. You'll see why on the HR diagram, or the first stage of life. And what's happening there? What's happening? What's the first thing that happens, no matter where a star is in that range of stars, is this. They're fusing hydrogen, turning hydrogen into helium. It's a big balloon factory. Stars start out life making balloons. I mean, they're celebrating, right? You become a star. You were a protostar, but you went on to American Idol, and now you're a star. Okay, so they do this in the all-gas core, the center. At the very, as you squeeze, the thing that gets really squeezed is that center, And it's all gas, right? There's no iron, don't think planets. This is a star. It's too hot for just imagine making a solid piece of ice hot, it becomes liquid, and make that hot, it becomes gas, right? So it's way too hot to be solid. And so it's all gas in the core. But what's happening is squeezed so much and it gets so hot that protons run into protons, as we said, and they bond. That's the simplest to fuse. Now, how many hydrogen turn into one helium? How many does it take? Well, if you look here and you go, okay, well, one proton and then two protons. So it must be two hydrogens makes a helium. That's wrong, not two. Makes sense. But remember, we talked a little bit about craziness about matter and light. Turns out that protons can turn into neutrons, and neutrons can turn into protons. And if you want to get into that, but the weak nuclear force, and people explore this stuff, right? There's a lot people didn't know, so it took a lot. So there's a process. You can look at the PP chain or other sequences. So there's all this stuff flying around. It's so fast that the hydrogen lost its electrons. I mean, they get ripped off, and so you have electrons flying around and all this. It's called plasma instead of really a gas, but ripped around. And so we still call it hydrogen, even though it doesn't have an electron. And through this sequence, this chain of events, some protons turn into neutrons. And so the answer is, and you probably saw that as a 4. Not 2. 2 is the wrong answer. 4 hydrogen, and just a little detail, right? So 4 hydrogen make 1 helium in this process. Every single star, I don't care how much gas you start out with, when you squeeze, that's the first thing that happens. And we're going to talk about that sequence in the next one. Let's finish this one off, and then we can get into some of those details and the different fusion cycles. But remember that by far, almost all of the lifetime is spent doing this for every star. Now, the lifetime will be much shorter for these big squeeze, much longer for these. Okay, let's do this. Cool. All right. All stars. Stars are nuclear fusion factories. Right? They're squeezing together things. I mean, if you squeeze those helium together, that's harder to do, right? It's harder to squeeze. Yeah, two protons, they don't like each other. They doubly don't like each other. That's harder to do. That comes later. When you squeeze that bag, if you're strong enough, first the easy ones go, right? Hydrogen into helium in the core. And then you keep squeezing, and once you get those snapped together, you start snapping other ones together, and the next easiest ones, and then the next easiest ones. Anyway, you start building bigger and bigger, or fusing together, larger atomic nuclei. And we have these different cycles, fusion cycles, or sometimes we call it stages of life, if you will. Until the squeeze isn't strong enough. What's that determined by? How much gas you have. How much gas, how much mass, how much gravity, right? So, and then when you can't, then there's death, and we'll talk about that. In each of these cycles, the star is in hydrostatic equilibrium. Static, not moving, equilibrium, balance. Hydro is, think of water, but fluid. Or you can call it, people call it gravitational equilibrium. Each fusion cycle or stage of life is in hydrostatic equilibrium until that cycle stage is done, and we'll talk about that instability and the processes next. So we got a gravity that's pulling in. We've got a big gas cloud, right? So we got some big gas cloud. How much gas? 75 Jupiters worth? 200 stars worth. Gravity pulls in. So I'll draw these arrows, meaning gravity is pulling this in, protostar, then it's going to start becoming a star, and then it'll go through different cycles. But for every single cycle, gravity's going to pull in. That will make the star collapse. When the fusion cycle starts, that creates sound that goes out. This fusion creates light, high energy light that pushes out. The light and gas pushes out. Gravity pull in, the light and the gas push out, coming from that fusion. So make that outward. Make an arrow for a push outward. Gravity pulling in, the fusion creating light, and the heat of the gas, the convection of the gas pushing out. And in every single fusion cycle, these, the in and the out, are balanced. And that's called hydrostatic equilibrium. And happily, our sun is in hydrostatic equilibrium. So next, we'll talk about our sun and its layers. And then we will talk about these cycles and the HR diagram and the death of stars.